All right, we're back. We're on page 2 of notes 8 of notes 8 of Calc C. We're talking about the alternating series test for alternating series. So it needs to strictly alternate, go positive, negative, or negative, positive, strictly alternate. We need the terms to decrease in magnitude or decrease in absolute value, and we need them to have a limit of 0. So this, I like combed through what the College Board uses in their explanation of convergent series on the free response questions, because I think that's like the safest way to go. This is the justification that they give. So the series has terms that alternate, decrease in absolute value, and have limit 0. Therefore, the series converges. So that's what we're going to write when a series converges by the alternating series test. So determine if the series converges or diverges. All right, so I'm going to say 1 definitely alternates. 2, they decrease in absolute value. So like you don't usually need to prove this. I'm going to say that terms decrease. All right, terms decrease in magnitude or absolute value. Check. And 3, the limit as n approaches infinity of 1 over n is 0. Check. All right, this converges. This is actually really interesting because if we took the absolute value of the terms, we would get 1 over n. We'd get the harmonic series. Harmonic series diverges. Now, this is the alternating harmonic. It's a famous series. It's the alternating harmonic. The alternating harmonic, it turns out, converges. And that's really interesting. So sometimes when it alternates, it will converge. If you get rid of the alternation, if you take the absolute value, it doesn't converge. That's going to be an important thing. So I'm going to say that the terms alternate, decrease in magnitude, and have limit 0. Therefore, this is the alternating harmonic converges by alternating series test, by AST. You can abbreviate it. Okay, and that's what we're going to do. We go through and we just make those decisions. It's pretty straightforward, I would say. So what I'm going to do, actually, so that I don't have to write everything over and over again, I'm going to like copy and paste some stuff here and just use this as sort of like a checkbox, and we'll go through and we'll see if it's true. Okay, so from 2 to infinity of -1 to the n natural log of n. Does it alternate? It definitely does, because -1 to the n makes it alternate. Terms decrease in magnitude. So 1 over the natural log of n. Natural log of n is getting bigger, which means that 1 over the natural log of n is getting smaller, so definitely decrease. And then the limit of 1 over natural log of n is definitely 0. So this thing definitely converges by the alternating series test. And so we should write that down. And so to write that down, I'm going to copy this and just kind of replace it. So I'm going to say that I'm just going to modify this to say the natural log of n. That looks gross. I'm going to fix that. Use some of the time I banked the natural log of n. All right. So the terms alternate, decrease in magnitude, have a limit of 0. Therefore, the sum from 2 to infinity is what happens when you try to copy. That's why, like, sometimes it's harder to copy than it is to just like do it. This converges by alternating series test. Definitely does. Okay, this next one, let me copy my criteria again. So you always want to think about this. Does it alternate? Do the terms decrease in magnitude? Do they have a limit of 0? Alternate, decrease in magnitude, limit of 0. You have to know those things. So here, let's erase our checkboxes and we will go through it. Does it alternate? It definitely does because of the -1 to the n. Now, does number 2 apply? Does it decrease in magnitude? I'm not honestly sure, but what I do know, so I'm going to put a question mark here because I'm not sure. What I do know, though, is that the limit as n approaches infinity of n plus 3 over n plus 2 equals 1, which does not equal 0. So that's a big X. So I don't need to deal with the decreasing part. So I'm just going to say that the limit as n approaches infinity of, I'll use the -1 part. I'm using the nth term test for divergence, basically. does not equal 0. Therefore, the sum from 1 to infinity of -1 to the n plus 3, n plus 2 diverges by nth term test. So always have that in the back of your mind. Like before you have to like wrangle with like, does it decrease, does it whatever? Before that happens, start thinking like, is the limit 0? Because if the limit's not 0, and that's probably easier to show, then the alternating series, it doesn't matter what alternating series test tells you, it already diverges by the nth term test. So always keep that in mind. Let me paste my criteria. Oh, I don't have it. Let me copy my criteria. This is gonna copy some weird stuff. That's all right, we can fix that. We got this, potentially. Okay, gone. Gone, 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 and gone. All right, so does it alternate? Yes, this is one of the weird versions of alternating. So when n is 1, cosine of pi is -1, then cosine of 2 pi is 1, 3 pi is -1, 1, -1, none, blah, blah, blah. So alternating, yes. Terms decrease in magnitude, yeah. So 1 over 3 to the n plus 2 is definitely decreasing, so for sure. And then 1 over 3, because remember, we're taking the absolute value of the terms. We're always talking about the absolute value of the terms, because I tend to think of it as like the terms themselves are like negative or positive. So then I think the absolute value of the terms is going to decrease, or the limit of the absolute value of the terms. This is definitely 0. All right, so we can copy, well, we can write our thing, right? The terms alternate, they decrease in magnitude, they have a limit of 0, therefore they converge by alternating series tests. So I'm going to copy this so that I don't have to write it over and over again. And like, yeah, it's annoying that you have to write it, but it gets it into your brain faster. So that's good. I'm going to redo some of this here. All right, so the sum from 1 to infinity, cosine of n times pi. I feel like pi times n makes more sense, but whatever. 3n plus 2 converges by alternating series test. Okay, so you just have to answer those questions. It's like a checkbox thing. Does it alternate? Do the terms decrease in magnitude? Is the limit 0? If so, converges by alternating series test. All right, let's look at this one. So I'm going to copy my criteria and then maybe edit my criteria a little bit so that I can check things off. Not a bad idea. Every time you do these, just write down the 3 requirements and see what happens. Okay, so is it alternating? Yeah, -1 to the n, definitely alternating. Do the terms decrease in magnitude? So the numerator of the absolute value is 1, and then this is going to get bigger, so 1 divided by bigger and bigger numbers gets smaller, so that's definitely decreasing. If your teacher is super picky, you might have to take a derivative and show that the derivative is always negative. You can do compare a sub n plus 1 to a sub n and do some inequality stuff and show that therefore a sub n plus 1 is less than or equal to a sub n. You could do that. You have a lot of options there. I don't make my students do that because I don't think it's really like the most important part of this test. But you know, your teacher might think that's important, and if so, you also have to think that is important. That's how school works. Like, you got to think the things your teacher thinks are important are important. This limit's definitely 0. So converges. Let's copy one of the answers. And then let's talk a little bit more about 2 of these. So duplicate you and replace your series with the correct one. So -1 to the n cube root of n plus 1. All right, so the terms alternate, they decrease in magnitude, they have a limit of 0, therefore the series converges by alternating series tests. It's like super nice. It's a really nice test to use because it's kind of like easy to apply, I would say. Interesting facts though. This, if it didn't alternate, would be 1 over the cube root of, basically 1 over the cube root of n, right? Basically a p series where p is 1/3, that should diverge. So the absolute value of the terms, you take the absolute value of the terms and add those up, you get a divergent thing. But when it alternates, it converges. We also saw that with this. This is the alternating harmonic. It's famous. So it's it might be famous well, I mean, it's like, it's one of those, like, you have the famous sibling thing. Harmonic. The alternating harmonic famously converges. The harmonic series famously diverges. It's a really good example to keep in mind, though, when you're like given a series and you're asked, like, does this converge? Does the absolute value of the terms converge? Like, what can you conclude? Blah, blah, blah. Like, alternating harmonic, classic example, because if you take the absolute value, diverges. Same thing happened here. In fact, with any P series, if we make it alternate, this is true. Every P series, if you make them alternate, they all converge. I think that's true. I think if you make any P series an alternating series by throwing in a -1 to the n, I think it will now converge by the alternating series test, because they'll have a limit of 0 for sure. They're all decreasing for sure, and then we just made them alternate. So yeah, so alternating is a difference, right? And then down here it just talks about harmonic and the alternating harmonic. So I will be back in the next video to talk about some more stuff, and I will see you there.